Good. Cool. So today what you're going to do is you're going to use the rational root theorem, and we're going to find possible rational roots of a polynomial. Now we know we can divide polynomials using synthetic division, and if the remainder is 0, then we know that that for a fact is a solution or a root. That's what we're going to be using today. To understand today's lesson, we need to really understand vocabulary so we don't get confused on what I'm saying. So everybody just look at some vocabulary. You don't need to take notes on this. I need you to just remember some vocabulary words. So if I say to you, find the roots, remember roots are the zeros of a polynomial, right? The solutions. Everybody agrees. Now there are two types of roots. There are real roots. Real roots will cross the x-axis. But there are also roots that are imaginary roots. These roots will not cross the x-axis. Now, the word rational. So we're going to be dealing today with rational roots. Now, rational means it can be written as a fraction. So look, I'm just showing you some examples. This is a rational number. This is a rational number. 3 is technically a rational number because it's written as a fraction as 3 over 1. So do you see how these are all examples of rationals? So if I said to you, here are the solutions of a polynomial, they would be rational roots. Does everybody agree? Okay, so that's what we're going to be dealing with today is rational roots. Fractional or whole number roots. Now one more thing to note, this really needs to sink in so this last part makes sense. If a polynomial is factorable, then it will have rational roots. Now think about why. If we can factor something down to linear factors, then when we solve for x, won't we get whole number or fractional roots? Does everybody see? So if it factors, it has rational roots. Does everybody understand? Because if it factors, we can solve for x, and that would give us whole numbers or fractional roots. Now we know if a polynomial is not factorable, this is when we have irrational roots, which would be examples. These are two examples of irrational roots, which can't be written as a fraction or imaginary roots. So if it doesn't factor, that's when we have imaginary and irrational roots. Does everybody agree? Cool. Now we can start the lesson. So 1-7, the rational root theorem. So everybody, when we have these huge polynomials, like look down here. If I said to you, find the solutions, when we have this huge polynomial, that's going to be rough to solve. First of all, for one, we don't know how to factor that. For two, it looks pretty ugly, doesn't it? Isn't there 7 solutions? Okay, so interesting enough though, we can actually solve this by guess and check. Now, guess and check would not take us all day long. How do we know what numbers to plug in? We don't. We would be, right now, if I just said guess and check, you would be trying out every number known to mankind, and that would take you the rest of your life. Well, guess what? The rational root theorem gives us a way to actually have less amount of guess and check. It gives us the possible rational roots of a polynomial. So that's what we're going to learn about first. Now that's saying this in way complicated form. So I'm just going to read a couple things, and then I'll show you what the rational root theorem is. So it says, factoring the polynomial, that's this huge polynomial where we have a leading term and a constant at the end, can be very challenging. In fact, sometimes we don't know how to factor it. Especially when the leading term and the constant have a bunch of factors. It's going to make it really hard to factor it. Now it says, the factors of number a sub n, so the leading term, factors of the leading term, and factors of the a sub naught. This is how you say a sub 0. Sometimes you call it a sub 0. Sometimes you can say a sub naught. It doesn't matter. But those two things can help you factor a polynomial. Isn't it true that with the quadratic we do what multiplies to be a times c? And that helps us factor it. Now, one way to find the root of a polynomial when the polynomial is set equal to 0 is to guess and check. But this is going to be very insufficient unless there's a way to minimize the number of guesses and checks. And that's where the rational root theorem comes in. So here is the rational root theorem. So it sounds complicated. I'm going to explain it more simply. But this is the rational root theorem. It says, let p of x be a polynomial where a sub n, x to the n, is the leading term, and a sub 0 is the constant. So it says, given that the polynomial has integer coefficients, there are a limited number of possible roots. So there are a limited number of solutions, you guys, when the polynomial is set equal to 0. So this is true. It is telling us integer roots, which are whole number roots, will be factors of your a sub naught. Any whole number roots will be factors of a sub naught. Did everybody hear that? And then also, any fractional roots or rational roots, any fractional roots will have the reduced form of p divided by q, where p is the integer factors and q is is the integer factors of a sub n. So let me put this in a little bit simpler terms here. Everybody look up here. So our constant is what we're going to call p. Our leading coefficient is what we're going to call q. Here's how the rational root theorem works. We can literally go through and list out all the factors of p. So what multiplies to be 10? Plus and minus 1, plus and minus 2, plus and minus 5, plus and minus 10. Does everybody see? Now we can also list out the factors of q. Plus and minus 1, plus and minus 3, plus and minus 7, plus and minus 21. Those all multiply to be 21. Now what happens is, any of our solutions, if they can be written as a fraction or as a whole number, any of those solutions will be some p divided by q. So you take all of your p's, divide it by all of your q's, and you list out all the possible solutions of the polynomial. So now we have a bunch of possibilities. Does that make kind of sense? So now we have listed out the possibilities, and now we can test those to see which one is an actual root by dividing by synthetic division until we get a remainder of 0. Sounds kind of complicated, but it's pretty easy. So we'll go through it and then you'll see what I mean here. So here's my first example, write it down. So now that you'll see an example, it'll make more sense, I promise. So it says, what are the rational roots of this polynomial? Now I want to point something out while you write it down. If I tried to say, okay, before today, I would try because there's 4 terms to factor by grouping. But then watch what happens. I get stuck because my safe haven isn't the same. Now, we all know how to factor by grouping, so I'm not going to go over that slow, but do you see how I'm stuck? The safe haven's not the same. It does not factor by grouping. So you'd say, dang nabbit, that doesn't work. Okay, well, we still have to be able to solve this. So what we're going to do is we're going to list out all of our possible p over q's. So everybody, once again, p is always your constant. Everybody, p. And our q is the leading term here. So we're going to go off to the side, and I always do p first because we're going to be doing p over q, and I like my work to line up nice and pretty. List out all the factors of p. What multiplies to be 5? Plus and minus 1, plus and minus 5. Does everybody see what I did? Yeah. Now let's list out factors of q. Plus and minus 1. What multiplies to be 2? Plus and minus 2. Now, the only possible rational roots of this polynomial will be some p divided by some q. So let's list out all the possible rational roots here. We got to take all of our p's and divide it by all of our q's. So let's go in order here. 1 divided by 1 is, so plus and minus 1. 1 could be a solution, or negative 1 could be a solution here. Now 1 divided by 2 is 1/2, so we also have plus and minus 1/2. You have to do every p divided by every q. Does everybody see what I did? Now let's go on to 5. 5 divided by 1 is 5. And now 5 divided by 2. All right. Now understand, if it's going to cross the x-axis and it's going to have a solution that can be written as a fraction or as a whole number, it will be at one of those places. Those are the only possibilities. So do you see how that narrows down which ones I guess and check with? Does that help? So now what you're going to do is you literally are going to test. You're going to say, okay, let's start with 1. Let's do synthetic division with 1. And see if we get a remainder of 0. If we do, we know for a fact it's a solution because it's divided evenly. So 1, draw in your line. Let's go for it. Here we go. 2, negative 1, 2, 5. Here we go. We drop down 2, multiply it up, add straight down, right? 1 times 1 is 1. Tell me if I make an error. 3. 3 times 1 is 3. We add straight down and get 8. So is my remainder 0? So we know for a fact x equal to positive 1 is not a solution. Let's try another one. Let's try negative 1. You guys do it on your own. Ready, set, go. You're going to be quicker than me watching me do it. All right. Did we all get a remainder of 0 for negative 1? So guess what? Yay! We know negative 1 is definitely a solution. It's a rational root. It's definitely a solution. Now, I can keep testing a half, negative half. I could test 5, negative 5. I could test 5 halves and negative 5 halves. That's one way of doing it. But also, now that we found one, didn't we take a cubic, divide it down, and now have a quadratic? Right? That's what we were doing last time, right? We took a cubic, divided it once, now we have a quadratic. It's way easier to look at a quadratic, in my opinion. So watch what I do here. So I'm going to say, okay, I have this new quadratic. Isn't that 2x squared minus 3x plus 5? Now what I'm going to do, and I need everyone to listen so it makes sense to you. If this factors, won't I have two more rational roots? If it factors, we have fractional or whole number solutions. If it doesn't factor, wouldn't I have to solve the quadratic formula? And quadratic formula gives me imaginary or irrational roots. Now read the instructions. It says, what are the rational roots? So if we have to solve this by quadratic formula, we can stop, because this would be the only rational root. Does that make sense? If it factors, let's just solve by factoring. Okay, so let's see if it factors. Here we go. What multiplies to be 8 times c? What multiplies, be very careful here, we almost made a mistake first hour. What multiplies to be 8 times c, which is 10, and adds up to be negative 3, and adds up to be b. Negative 5 times 2 is what we said in first hour. But that doesn't work, because you're right, negative 5 times 2 is not positive 10, so it doesn't factor. The quadratic doesn't factor, so we do not have any other rational roots. Does everybody agree? So now we have answered the question. It said, what are the rational roots? That's the only one. Sweet. Any questions on that? Making sense? Okay, cool. So this is obviously the least, we like this one the least. But once again, if it doesn't factor by grouping, you have to solve using, oh dang nabbit, P over Q. Okay, go to number 4. Go to number 4. Here we go. So negative 1 was the answer, and then it said list out the possible rational roots. So we actually had, here's my possibilities, and then this one was the actual. So that's kind of how we would answer it. Here we go. Go to number 4. You got to go a little bit quicker. So here we go. Because lunch is going to ring in 5 minutes. Listing out factors of P. This is P. Plus and minus 1, plus and minus 2, plus and minus 4. Does everyone agree? This is Q. Let's list out factors of 12. There's a lot. Plus and minus 1, plus and minus 2. Plus and minus 3, plus and minus 4. Yikes. Plus and minus 6, plus and minus 12, right? So now let's list out all possible P divided by Q. Here we go. 1 over 1 is 1, right? 1 half. Look, 1 half. Now 1/3. Now 1/4. Now 1/6. And 1/12. We've done that P divided by all the Q's. Now let's do this one. 2 divided by 1 is 2. 2 divided by 2 is 1. We don't need to list it. We've already got it. 2 divided by 3, well, we don't have that one, so we've got to list that. 2/3. 2/4 is a half. We've already listed it. 2/6 is 1/3. We've listed it. 2/12 is 1/6. We've listed it. Does everybody agree with what I'm doing here? Now do 4 divided by 1. Now 4 divided by 2 is 2. We've listed it. 4 divided by 3, we need it. 4 divided by 4 is 1. 4 divided by 6 is 2/3. We've already listed it. And 4 divided by 12 is 1/3. We've got it. So these are the possible rational roots. That's a lot of numbers. So I could go through and test using synthetic division every one of these, okay? But now, because there's so dang many, I'm going to kind of let you cheat. What I want you to do is grab your graphing calculator and hit graph this function, and see where it looks like it might be crossing so that we know which one to test. Does that make sense? There's so many. We're going to be testing all day long if we just start. So take your calculator, graph it, and does it look like it's crossing at a half? If it does, we better check for sure. You have to check using synthetic division. So everybody go. Tell me where it looks like it might be crossing so we know which ones to check. Oh, you probably knew that. She says that it looks like it might be crossing at -1/3. Okay, let's try that one then in a minute. Any others that we should be trying? 1, okay, let's try out 1. And then, doesn't it kind of look like maybe -1? Or no? Am I crazy? No? No, definitely not -1, or you mean no, I'm not crazy? Definitely not -1, okay. Any others? No? Nothing else that looks close to any of these values? 2/3? Okay. 2/3. Let's try those out. Ready, set, go. Everybody pick one and go. Test out one. Let's all take one and test it out. Does the remainder come out 0? If so, it's a solution. So 1 is not. Okay, so we can say, okay, nope, 1's not. Anyone else? Guys, these were tested, and guess what? Negative a third didn't work, and neither did 2/3. Now, we've tested all the values that we feel like it could possibly be. Well, let's say we were unsure. We could then spend 20 minutes testing every value. None of them work. None of them when you divide the remainder 0. So that means this one, this polynomial has no rational root. So our answer was, okay, which makes sense. I mean, we can have irrational roots. So even though it crossed the x-axis, it was crossing out a place, like, for example, 2 plus root 3 as a decimal that crosses the x-axis, but it's not rational. So yeah, it has 4 solutions. They're just not necessarily rational. They're not rational, or they would have been in this list. Does that make sense, everybody? So our answer is, here are the possibilities, but there are no actual rational roots. Can you try some on your own? Okay, so what I want you to do is, in your group, do problems 1, 3, 5, and 6. And it's okay not to split up the numbers. Everybody work on number 1 together. But it's okay to say, you test 5, I'll test -5. Does that make sense? So work together and get through some of those. Ready, set, go. Section, you can always go back later. Okay. So it says, right now we're learning is a bunch of theorems of polynomials. So we just learned the rational root theorem. Now here's the conjugate root theorem, which we've already talked about in here. The conjugate root theorem says that if we have an imaginary root or an irrational root, then its conjugate must also be a root. Conjugate is only a change of sign in between terms. So if x equals 2 minus root 5 is a solution, what do we know even though it doesn't say what else is a solution? 2 plus root 5. Very good. What if this would have been negative? Does that become positive? No, still would have been negative. Just make a test in your knowledge here. Once again, if we have an imaginary solution, its conjugate is a solution. So 2 minus I would also be a solution. Do we all agree? That's all it asks. What other solutions do we have? Well, I've answered it, haven't I? Now, what does it ask? You've got to read your directions. So, for example, it says, write the polynomial with these given roots. So we have x equals 2. Should I write x equals -2? No, conjugate roots doesn't work with whole number roots. It only works with imaginary or irrational. So we can't say for sure that -2 is a solution. Does that make sense? But if x equals 2i is a solution, what else is a solution? -2i. Now remember, this says, what's the polynomial? It should say in standard form. So let's work backwards. Shouldn't I be making this equal to 0? So we have x minus 2 equals 0. Let's make this equal 0. Minus 2i minus 2i. So we have x minus 2i equals 0, and then we'll add 2i, right? We've done this. X plus 2i equals 0. Now you'd say, before they were split apart, they used to be multiplied together. Now everybody take my strong suggestion. I promise you, if you're multiplying 3 things together, you should multiply 2 of them together and then combine like terms and then multiply it into the third. You're going to probably most likely get it wrong if you take this and multiply it to this. Well, just because it's easy to make errors. So here's what you should be doing. Anytime you're multiplying conjugates, multiply those together first. Did you all hear the rule? So that you'll get it right. Okay, so you're going to say, I'm going to focus on these two. X times x is x squared. So we have plus 2ix minus 2ix, which makes sense because the conjugate middle terms cancel out. Isn't that what the definition of a conjugate is? And then we have minus 4i squared. Does everybody agree? Now you'd say to yourself, okay, so I really have x squared minus 4i squared. Isn't I squared equal to -1? So isn't that x squared plus 4? -4 times -1 is positive 4. So you'd say I have x squared plus 4, and I really have that multiplied to x minus 2. And now it would be good to distribute root to all of it. X times x squared is x cubed. Plus 4x minus 2x squared minus 8. Cool. Rewrite it in standard form. X cubed minus 2x squared plus 4x minus 8. I want you to notice something. What we did in the last unit, which we just tested on, was we said, given this polynomial, solve. So what method would you use? Grouping. You factor by grouping, and then you'd go through and you'd end up with those solutions. Does everybody see what I did? Does that make sense? We just went backwards, but we wouldn't know how to solve it if we needed to, which wouldn't we get those solutions at the top. Sweet. There's our polynomial in standard form that had those solutions. Okay, let's do number 15 off the worksheet. Here we go. Write the polynomial with these given roots. So you would say to yourself, okay, cool, x equals 3i, so even though it didn't say, what else is a solution? Negative 3i, x is equal to root 6, which is irrational, therefore negative root 6 is also a solution. It wants it in standard form, so I'm going to work backwards. Now think about it, I'm going to have minus 3i, x minus 3i, right? I'm not going to go through, I'm not going to write it down. Is anyone mad if I go x minus 3i? And then we'd add 3i, so x plus 3i, to make it equal to 0. Subtract root 6, wouldn't we? X minus root 6, and then you would add root 6. So you have x plus root 6. Anytime you're multiplying four things together, multiply 2 together, multiply the other 2 together, and then multiply it all together. You should always multiply conjugates together. So focus on multiplying those two, focus on multiplying those two. Let's do this quickly. X squared, right? Now think advancedly. The middle term cancels out, so do I need to write it? No. And then we have minus 9i squared. So isn't that x squared plus 9? Okay, let's do this next one. X times x is x squared. Once again, conjugates, middle terms cancel out, so I'm just going to do that one in my head. Now right here, watch very carefully. That's a minus root 36, because 6 times 6 is 36. So what does that become? X squared minus 6. And now it would be appropriate to then multiply those two polynomials together. That's a times sign. X squared times x squared is x to the 4th minus 6x squared plus 9x squared minus 54, combine like terms. X to the 4th plus 3x squared minus 54. And look at that, we got a polynomial that we learned how to factor by U substitution, didn't we? Sweet. So we learned how to solve this in the last unit, now we're kind of going backwards. Yes. So there's a difference between when we solve and when we simplify radicals. So if I said to you, what's the square root of 4? You would say 2. It's a primary root. And if I was solving x squared equals 4, we're looking for all the values that'll make this true. That's why we have to put plus and minus versus just simplifying. So fun fact for you, square root of 4, we would just put 2. But solving, we need both. Good question. Valid question. So, all good? Okay, do 17, 7 through 18. Make sure you read the directions because look at problems 7 through 12. All it asks is what other zeros do I have? Don't go too far or you're doing extra work. So a lot of people mess up on 16. Let me show you what they do. They go like this. Oh, so we have 2 plus I times 2 minus I times 1 minus root 5 times 1 plus root 5. Where the heck's the variable? This is going to be a major issue if we do that. Does everybody agree? You forgot something. You have to say x equals 2 plus I. Solve for x. Shouldn't I be subtracting 2, subtracting I? X minus 2 minus I is a heck of a lot different than 2 plus I. Then we also have x is equal to 2 minus I. So now solve for x here. Wouldn't we subtract 2 plus I? Yes. So we're going to have x minus 2 plus I. That's what we're going to be multiplying out. Don't do that. Does that make sense, everyone? Sweet. Same thing with that one. That was going to be kind of ugly, but I know you can do it. You've got to be really careful. Multiply the conjugates together. It should come out rational coefficients. So if you still have an I, you've made an error somewhere. It's a good sign to you that you messed it up. Okay. They're going to come out gorgeously. I'll be honest with you. Continue on that section for another 3 minutes, and then we got to move on. Okay, so now we're going to talk about Decartes' Rule of Signs. So Decartes' Rule of Signs is another way to help us find out the real roots a little bit quicker because it helps us using Decartes' Rule of Signs with the rational root theorem. We're able to say which one should we test first. If I didn't allow you to have a calculator to kind of cheat, we would want even more help. So this is a fun fact for you. So René Descartes is a French mathematician back in the 1600s. When he was 8 years old, his father sent him to college. He was only 8 years old and he was in college. And he was actually, back in the day, if you got sick, there wasn't modern medicine, obviously. So he was actually pretty sickly, but he was at college because he was a really smart kid. And so he would lay in bed and study, and the professors would let him. But other students would have to go to class. But he could lay in bed and study for the first half of the day since he was pretty sickly. So also, he was not only was he a mathematician, but he was a philosopher, and he also got a law degree by the age of 22. He graduated law school by age 22, so kind of interesting. Very smart man. Now, law school, if any of you are interested in possibly becoming a lawyer, it takes a lot, it takes a math brain a lot of times because it's very logical. You should look at a LSAT exam, a pre-law exam. They'll do a lot of logical thinking. If Johnny crosses the road at the same time as Susie, and Susie crosses across Johnny, and dilly-dally later, who crossed who at this time? Like, very much logical thinking happens on LSAT exams. So he was a very logical thinker. Anyway, kind of interesting. So, one thing he was doing is he was sitting there studying polynomials, obviously without a calculator from back in the day, and he was looking at polynomials in standard form. And he started to notice something. And then he's like, this always works. And then he came up with a proof for it because it does always work. So this is what he noticed. What Renee noticed is that the number, if a polynomial is in standard form, he noticed that the number of sign changes between positive and negative, between terms, the number of those can tell you how many positive real roots you're going to have and how many negative real roots you're going to have. So what he noticed is the number of positive real roots when the polynomial is set equal to 0 is either equal to the number of sign changes between consecutive numbers or is less than that by an even number. So we subtract 2. So if there was a sign change from positive to negative 2 times, guys, that means there's 2 positive real roots or 0 positive real roots. And he noticed that that always works. Does that kind of make sense? We'll go through an example. Then he also noticed, well, what about negative solutions or negative roots? So what he noticed is the number of negative real roots. Now, guys, so do you see what I hear where it crosses? That would be a positive real root in the positive x-axis. Does that get it? Do you get what I'm talking about? Then do you see how these are negative real roots? They would cross over in the negative x-axis. So what he noticed is if you plug in negative x to say, let's look at negative x, you simplify the polynomial. Once again, the number of sign changes between consecutive terms with the number of times it's going to cross in the negative axis. Does that kind of make sense? And then we'll do an example. Kind of? Okay, it's going to maybe take an example. Okay, here we go. So it says, what does Decartes' rule of signs tell you about the real roots of this polynomial? So what we can do is use Decartes' rule of signs to figure out how many possible positive real roots we're going to have and how many negative real roots we can have. So what you do is you literally count how many times it changes from positive to negative between consecutive terms. So let's look at this. You see how we start out from a positive and then it becomes negative. That's one sign change. Now from a negative to a positive, it happened again. So we know that there is either 2 real positive roots or 0. So it's going to cross the x-axis in the positive x-axis twice or none, for sure. Does everybody get it? Now the negative x-axis, let's see. So to test that, you actually have to plug in negative x. So let's resubstitute in negative x. So look, negative x cubed minus negative x squared plus 1. You see how I plugged in negative x? Kind of like when testing even or odd, right? So let's think very carefully though. Negative x cubed is negative x cubed, isn't it? Now don't look at this negative because that might throw you off. What's negative x squared? Positive x squared? So it'll be minus x squared plus 1. Now let's see how many times it changes from positive to negative. Negative to negative? Nope. Negative to positive. Yeah. So guys, there is one negative real root. It's crossing the x-axis once, for sure, in the negative x-axis. Does that make sense? So did you see how that might help us? Shouldn't I test all my negative values first, since it's going to cross the negative x-axis once for sure? So it kind of helps me narrow it down. Now, these aren't necessarily rational, though. That's the other catch. They could be irrational. Like negative 2 root 3. Isn't that a negative number that crosses the x-axis in the negative vicinity? So they're not necessarily rational, but still it helps us determine, well, maybe we should test out the negatives first. Now look, I'm going to show you that same polynomial graph. Look, there it is. Didn't what Renee said would happen? 0 positive real roots, right? And 1 negative real root. It always works for all polynomials. Okay, go to number 19. What does Decartes' rule of signs say about the number of possible positive real roots and the negative real roots? So let's hurry and list out how many possible positive real roots this polynomial will have for sure. So we're going to test the sign changes or count them. Positive to positive. Nope. Positive to negative. And then negative to negative. So we know for a fact this has one real positive root. All right, let's test negative. Before we can do that, we've got to plug in negative. So let's go 3 negative x cubed plus negative x squared minus 8 times negative x minus 12. The trick is simplifying that correctly. Now think about it. A negative raised to an odd is a negative. So that's negative 3x cubed. A negative squared is positive. So plus x squared. A negative times a negative is positive. Let's count how many sign changes now. Negative to positive, 1. Positive to positive doesn't count. Positive to negative, 2. So this has 2 or none negative real roots. It's going to cross either twice or none in the negative x-axis, and it's definitely crossing once on the positive x-axis. So now if it was me and I was trying to find possible rational roots, I would test all my positive ones first. You see why? Yes. True. If you think about it, that is true. I see what you're saying. So do you guys see what he's saying? Since there's 3 solutions, he's putting logic together. Well, if there's one real positive, then there has to be 2 or none negative. True. True. Yes. Yes. Because there's 3 solutions, right? What if we have 2 imaginary solutions? Wouldn't it never cross again? We have 1 real positive, then we could have either 2 more roots that cross or 2 that don't. Does that make sense? So it goes down in 2s no matter what. Okay, let's do okay, so now we're going to use the rational root theorem and Decartes Rule of Signs to kind of narrow down what real roots we will have and kind of test. So go to 23. It says find all the possible it says find all the rational roots when the polynomial is set equal to 0. So the first thing we would do is say, okay, let's list out all of our p over q's. So here's q, here's p, list out factors of p. Plus and minus 1, plus and minus 2, plus and minus 4, factors of 8, plus and minus 8. Factors of q, plus and minus 1, right? So all possible p over q's, obviously anything divided by 1 is just itself, so plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8. Now before we learned Decartes' Rule of Signs, we would just start testing values. Let's pretend I said no calculator on this problem. Now let's say, okay, these are the ones, I don't want to have to test all of those, or I'd like to do this in the quickest way possible. So let's now look at Decartes' Rule of Signs to see how many positive real roots we're going to have. So let's look. Positive to negative 1, right? Negative to positive 2. Now look, positive to positive doesn't change. So we're going to have 2 or 0 positive real roots. Let's do negative. Now if you don't mind, I'm going to do it in my head without actually plugging it in. Is anyone going to be bothered? So negative x cubed, won't that become negative x cubed, everybody? And then, I'm not going to look at negative 5. Negative x squared, isn't that positive x squared? So it'll still be minus 5x squared. Then we have positive 2x times negative x, if I was plugging in a negative x, so minus 2x plus 8. So let's count how many sign changes. Negative to negative doesn't count. Negative to negative doesn't count. Negative to positive, yes, 1. So we know for a fact there is 1 negative real root. So what I'm going to personally do is instead of testing all my positives, I'm going to test negatives first. Does that make sense? Let's test negative 1. If negative 1 doesn't work, we'll test negative 2. Here we go. Negative 1. Let's quickly do this. 1, negative 5, 2, and 8. If I said don't even touch your calculator, in fact, put it under your desk. So we add straight down. 1 times negative 1 is negative 1. Add straight down is negative 6. Negative 6 times negative 1 is 6. We add straight down and get 8. 8 times negative 1 is negative 8. Add straight down is 0. Sweet. So now what we would say is, okay, cool. So we have x is equal to 1. Negative 1. Okay, very good. X is equal to negative 1. Now I need you to listen very carefully. Think about this. Will I have any of my other negatives be a solution? No, because we knew there was only 1. So now do you see how we do not even have to test negative 2, negative 4, or negative 8? So now I could test all my positives, couldn't I? Because there could be 2 or there could be 0. But I'm personally going to do this an easier way instead of testing them all, which would be fine. I'm going to say I took a cubic, I divided, and got a quadratic. So let's see if the quadratic factors. If it factors, there'll be 2 more rational roots. If it doesn't, we found them all. So x squared minus 6x plus 8, does that factor? Well, multiplies to be 8 and adds up to be negative 6. Negative 2 times negative 4. So then it quick factors to be x minus 2 and x minus 4. So what are my other 2 solutions? 2 and 4. So we could have tested those and got with synthetic division and also got the same conclusion. However you want to do it. Does that make sense? Okay, sweet. Do you want to do another one?
Yep.
Okay, go to 25. Let's go to 25. Here we go. So we'll do all of our possible P over Qs. Factors of 12. And I'm listing them out. This is going to have a little bit more. All possible P over Qs. 1, 1/2. 2. 2 over 2 is 1. We've already listed it. 3. 3 over 2. 4. 4 over 2 is 2. So we've already listed that one. 6. 6 over 2 is 3. We've already listed 3. 12, and then 12 over 2 is 6, and we've already listed that. So these are the possible rational roots. That's quite a few. Now let's use Decartes Rule of Science to see if it's positive or negative. That we should test first, is what I mean by that. So positive to positive. Nope. Positive to positive, no. Positive to negative, 1. There is 1 positive real root. Okay, cool. Let's test negative. So once again, won't that become negative? I plug in negative x. So that would be negative 2x cubed. Plug in negative x. So that would be still positive 13x squared minus 17x, because we're plugging in negative x, and then minus 12. Let's check. 1, 2. Isn't that it? So there's 2 or 0 negative. So now, I would never be this mean, but let's pretend on the test I said, okay, no calculator for this one, so I would test positives first. Agreed? Yeah. But that's enough where I'm going to say, go ahead and use your calculator. Which ones possibly should we test first? Graph it and see where it looks like it's crossing, so that we know which one we should maybe test first. Anyone? Any whole numbers? Okay, you said you would test negative 4, you said negative 3 and 1/2. Cool, so you would go through and test those. Everybody go. You're going to be quicker, we're going to be quicker to split this up. Somebody take negative 4, somebody take negative 3, somebody take 1/2. Everybody choose one and go for it. 1/2 works. So x equals 1/2 is an actual solution. And then also negative 3 works. You're right. And also negative 4 works. So you were right. Awesome. We found them all. Now how do I know I definitely found them all? Degree 3. So haven't I found all the solutions? Okay. Sweet. Okay, cool. That is it. So that's all you have to do here. I'm going to have you cross out a few though. No, not these. Erase. Okay, what I want you to do is flip to the back page. We have enough practice without doing these ones. So cross out 35 through 40. You will never do those. Yep, cross out 35 through 40. We have enough practice without those.